morning, students. Welcome to a session on relation. I will define what a relation is. As the name indicates, a relation is nothing but a link between objects, a correspondence between some entities. So all real-time entities that are linked between them, that have correspondence between them, can be represented mathematically by means of relation. Now I am going to define relation mathematically. Now what is a relation? A relation is nothing but a subset of two non-empty sets. Okay? And how is it represented? It is represented by means of a Cartesian product of two sets. I'll show you an example. Say let's take up two sets. A is equal to 3, 6, 9. B equal to I have 15, 12 and say 81. These are two sets. I have written the two sets in the form of a roster form. There are 3 elements present in set A and there are 3 elements present in set B. The elements of set A can be related to the elements of set B, and that relation that I am showing, I show it by means of relation. So relation in mathematics is represented by the alphabet R. Is represented by the letter R. So R is a subset of the Cartesian product of two non-empty sets, namely A and B. Look at the way I am writing it. I have written it in caps. You already know that. In set theory you have studied this. When I want to name a set, I should name it in capital letters so that you are clear. So R is a subset of A cross B. Now I define A cross B in the set builder form. What is A cross B? This is not multiplication sign. It is a Cartesian product of the set A and set B. So what is A cross B? A cross B consists of elements, and the elements are ordered pairs. So the first element comes from set A, the second element comes from set B. So it is A comma B, ordered pair, such that A is an element of set A and B is an element of set B. That's it. So from this definition, what do you understand? This Cartesian product is also a set. When I mean it is a set, I write it within curly braces. This is very important. And I have defined this Cartesian product by means of the set builder notation. So it consists of ordered pairs A comma B, where A is an element of A and B is an element of, say, capital B set. Now how many elements will be present in A cross B? The maximum number of elements that will be present in A cross B, or the cardinal number of A cross B, that we should know. Before that, you all know that the cardinal number of set A is equal to the number of elements present in set A. This is how we write the cardinal number of set A. How many elements are present in set A? 1, 2, 3. Therefore, we write it as 3. The cardinal number of set B is equal to, once again, 1, 2, 3 elements are present, and therefore this is 3. Now, I am showing a relationship between the elements of set A and elements of set B. How many relations? Okay, what can be the number of cardinal number of A cross B? Now, cardinal number of A cross B is equal to cardinal number of set A into cardinal number of set B. So what is the cardinal number of set A? It is 3 into 3. So what is it? It is 9. It is 9. So to generalize this, how can we generalize it? Say, if set A has got, say, n of A is equal to P. If set A has P number of elements and set B has Q number of elements, then cardinal number of A cross B will be equal to P into Q. P into Q, which is nothing but the cardinal number of A set and the cardinal number of B set. P into Q. The cardinal number of set A and cross set B is equal to PQ, which is nothing but P into Q. I told you the cardinal number of the set relation is equal to 3 into 3, which is equal to 9. Now I will show you how I am going to form the relation. So A cross B is equal to, since it is a set, we need to write it within the curly parenthesis or curly braces. The elements within the set are ordered pairs. The elements of the set are ordered pairs. So, I am going to link 3 and 15. Then, 3 and 12. Then, 3 and 81. Then, 6 and 15. 6, 12. 6, 81. 9, 15. 9, 12. 9, 81. And close it with the curly braces. Now count the number of elements present within the set. There are 9 elements present within the set. So, from this we conclude that the relation R, okay, may be equal to the Cartesian product of A cross B. So, A cross B, I have shown you the maximum number of combinations that I can make between the element of set A and element of set B. Therefore, it is 3 into 3, which is equal to 9. In the previous example, I showed you the maximum number of combinations that I can make between the elements of set A and set B. Now, just look at this formula. A relation can also be a subset of, it can be a subset of the Cartesian product of A cross B. So, A cross B, I showed you 9 elements being present. Now, I am going to show you another relation. So, it can be, so, since it is another relation, R1 can consist of ordered pairs like this. Say 3, 15, 3, 12, 3, 81. So this relation consists of only 3 ordered pairs. Likewise, let me show you another relation. R2. Okay. I am going to show another relation. So 6, 12. So this relation consists of only one ordered pair, only one relation. Let me show you another example, R3. Look at this carefully. Okay. So this consists of 9, 81. So this consists of only one ordered pair. Likewise, I can write or I can frame any number of relations. This is an example that I showed you to, Okay students, look at these 3 relations. It is something meaningful, right? Okay. When you take up the first relation R1, look at the ordered pairs. The first element is related to the second element. By how? 3 into 5 becomes 15. Likewise, look at the second ordered pair. 3 into 4 is 12. Likewise, you can multiply this also. Am I right? So, this has got some meaning. Look at the second relation. 6 into 2 is 12. Third relation. 9 into 9 is 81. So, these are some meaningful relations that I have shown you here. From these examples, you'll be able to understand that R can be a subset of A cross B. These were the ordered pairs that were present in the whole set A cross B. Just relook into it, you'll see that all these ordered pairs were present in A cross B. From A cross B, I am taking only certain ordered pairs and I am naming it as R1, R2, R3 and so on. Okay? And therefore, these relations are a subset of A cross B, I will say. So I hope you are clear with that. Now I am going to generalize it. What am I going to generalize? How many such relations can I frame with these 2 sets? Okay, that is what I am going to generalize. So, the maximum number of relations that could be framed is equal to 2 to the power of P into Q. 2 to the power of P into Q. So here what is P? P is nothing but 3. Therefore 2 to the power of 3 into Q. What is Q? Q is once again 3. So what will be the answer? 2 to the power of 9. You calculate what is 2 to the power of 9. That number of relations you can frame with, say, set A and set B, which has got 3 elements and 3 elements. Okay, let me show a simple example here, and through this you'll be able to understand what I taught you prior. Okay, so here set A consists of only one element and it is a singleton set. Set B consists of 2 elements. Okay, so what is the cardinal number of A? Cardinal number of A, which we represent by means of P. So P is equal to what now? It is 1 here. P is equal to 1 here. And then what is the cardinal number of set B? Cardinal number of set B is equal to 2 here. So 1 and 2. So what will be the maximum number of relations that I can say develop, or I can frame using the elements in set A and B? It is nothing but 2 to the power of P and Q, which is equal to 2 to the power of, here P is equal to 1 into, say B is equal to, Q is equal to 2, and therefore it is 2 to the power of 2, which is equal to 4. In the next slide, I will show you what are the various relations that I can frame. And you see, you can, at the maximum, you can frame 4 relations using these 2 sets. Okay? Just look at this slide. What is the Cartesian product of A cross B? The Cartesian product of A cross B is nothing but 3, 15 and 3, 12. Okay? So how did we get it? The cardinal number of set A into cardinal number of set B, which is equal to 1 into 2, which is equal to 2. So it consists of only 2 elements. So based on this, how many relations can I frame? That also we saw the formula. What is the formula? 2 to the power of P into Q. So what is the value? 2 to the power of 2 is nothing but 4. So I have 4 relations. I'll show you the 4 relations. So R1 is equal to, just I am relating 3 and 15. It consists of only one ordered pair. Then take R2. R2 I am relating only 3 and 12. One ordered pair. Then R3 I am relating 3 and 15 and 3 and 12. So 2 ordered pairs. And R4, it is nothing but, I don't have any relation. It is an empty set. So these are the 4 maximum number of relations I can frame using this example, where my P is equal to 1 and Q is equal to 2. So I'll conclude this session with some real-time examples for you. Okay? The examples, 2 examples that I showed you may not look significant. Okay? Certain relations had some meanings, but certain relations you didn't have any meaning. I just related the first element and the second element. That's it. Now I'll tell you some real-time examples that are present. Okay, let's take up this example. Just listen to the narration that I am telling you. I hope you know what a femur bone is. I hope you know what is a femur bone. A femur bone is the bone which connects your hip and your knee. There is a finding from this femur bone. It is being found that in ladies, the length of the femur bone is related to their height of the lady. Okay, so every woman in this world, okay, their height can be calculated or manipulated if the length of their femur bone is known. So what do you understand? There is a relation existing between the length of the femur bone and the height of the lady. There is a correspondence between these 2 entities. So what is a relation now? A relation is, okay, a link between 2 variables. A correspondence between 2 variables. Why do I call it a variable? I call it a variable because the femur bone length keeps on varying from a woman to another woman. Likewise, the height of the women also varies, and therefore we call it a relation between 2 variables. Understood? Let's take up another example. Okay? Now, the humidity of a particular area determines its temperature. It varies from place to place. So, at Chennai, based on the humidity at Chennai, the temperature is being defined. And this varies for every hour. So, this also is possible to be studied. So, based on the humidity, the temperature varies for every instant. So, this is also a relation. We can show it by means of a relation. So let's close this session with one more example. Let's take up our country, India. There are many states in it. And from every state, a set of people or say member of parliament, we call them MPs, represent that particular state to the parliament. Say let's take up Tamil Nadu. From Tamil Nadu, there might be say 15 MPs representing Tamil Nadu in the parliament. Say Maharashtra, there might be say 25 MPs representing Maharashtra in the parliament. So this also varies. The number of say member of parliament in every state varies, and we have the next one, which is nothing but the different states being presented. So there's a relation between the state and the number of MPs in that state. So what is a relation? A relation is a set of ordered pairs. And how do you find the set? How do you frame the set? It is by means of the Cartesian product of the two sets involved in that particular problem.